Hello, everyone. This is section 7.2. We now start the methods for finding antiderivatives. All right. So in chapter 6, we were introduced to the idea of antiderivatives, very simple ones, power rules, and the one-step rules, which we're going to use a lot in this one, actually. I think I might have even mentioned back then that all of our methods kind of dwindle it down to try to use methods we already know. So this first method is called U substitution. I'm going to walk you through kind of a proof at the beginning. You can probably not take notes if you're writing stuff down until I tell you if you want. U substitution is basically a way that helps us deal with a chain rule. So this is kind of like working backwards in the chain rule. I could just start doing examples and you'd probably get it, but I just want to show you kind of where it comes from. So what you see here is a chain rule, basically. Okay. F of g of x. I call it big F for a reason. Okay. So what I did was I started with a composite function. Okay. And I'm kind of working backwards. So I'm taking the derivative of that composite function. So what you're seeing in this first step here is the chain rule. It's f prime of g of x times g prime of x. That is the chain rule, right? And then since I used a big F to treat it as an antiderivative, that big F prime becomes a small f. That's what you see here. Okay. Next step then is so basically what I have is this, I guess. I have this equals this, right? That's what you see right here. Derivative of big F equals that. So now I'm kind of going to work backwards with derivatives to show, or antiderivatives to show you how I can deal with this in a problem. So I just integrating both sides right now. So the integral of the derivative of big F of g of x equals the integral of f of g of x times g prime of x. So I'm taking my chain rule just now, I'm working backwards. The integral of the derivative of big F is just big F. I just left the other side alone, notice. Okay. And now this is why we call it U substitution. So we're just trying to go, well, how do I integrate this thing? I got f of g of x times g prime of x. So if I do what's called a U substitution, I let u equal g of x. So in essence, that's a u right there, the g of x, which also means du is g prime of x. So this is a du, right? So what happens when I rewrite it then is it gets rewritten as the integral of f of u du. So now it's like one variable, one function, no composite function anymore, right? And that equals the integral that's on the other side, which is big F of g of x plus c. So the idea is this basically, is if I'm trying to integrate something, I can do what's called a U substitution. So that was just kind of a walk-through process. It's not super important. Most people don't really kind of grab what's going on. I'm going to do as many examples as I can in like 15 minutes. And I think you'll kind of get the handle of it doing it that way. So here's an example. So basically, as a reminder, a U substitution is a way to deal with a composite function. All right, looks like a pretty simple problem here. It's the most basic U substitution here. But it's a composite function, right? So it's something to the 1/2 power, but it's not x to the 1/2. If it was x to the 1/2, I could just take the antiderivative. That'd be x to the 3/2 over 3/2. But because there's something inside of that, I can't do it that way. It's just like derivatives. It doesn't work that way. So what I do is what's called a U substitution. I make U equal to something in the problem. And if you go back to the original steps, I don't want to spend a ton of time going back to this because I think you'll go away from it eventually. But at the beginning, it can be kind of helpful to just kind of work backwards and think, I need to pick something to be my U. Okay, well, what am I going to pick to be my U? That's the hardest part of these problems, is deciding what to pick for U. Typically, you let u equal the inside part of the composite function. Doesn't always work, so I don't want to say always. The inside part of the composite function, right? So in this case, that's the 5x plus 7. So what you do is you pick something for you. You're going to pick wrong at times. Sometimes, if all else fails, just guess. But to start with something, you always probably want to start with the inside part of a composite function, because that's how you determine what you're going to use sub. The first day we do use sub be pretty easy because that's the only method we have. But as we start to learn other methods, it can be a little bit trickier knowing what method to use. So you will have to do a little bit of guessing and checking, trying. Sometimes you pick the wrong thing for u, it won't work. So we let u equal 5x plus 7. Once you pick your u, what comes next is finding your du, because notice I'm going to let u equal g of x, and then du is g prime. We just take the derivative. So the derivative of 5x plus 7 is just 5. The dx is just an operator. It changes the operator. It's kind of like differentials. Think about that as being differentials, which is in essence what it is. We're not approximating anything with this because we don't have numbers, but it's the same basic idea. So now what you do is you go back and you substitute what we just did. Right. I actually did one other thing first. I take my, I solve this for dx, because notice when I substitute, I have a dx. That dx turns into that 1/5 u. And then that 5x plus 7 turns into u. So what this substitution has accomplished is two things. It's changed the variables, which isn't a great accomplishment. But more importantly, it got the composite function part out of it. So notice now I just have a nice little problem that's 1/5 u to the 1/2. I changed the variables, so I'm going to integrate with respect to u. So the integral of the 1/5 is a constant, right? So that 1/5 is just hanging around. The integral of u to the 1/2 is u to the 3/2 over 3/2, or times 2/3. So you get 2/15 times u to the 3/2. But remember, we made a substitution, right? So that we have to get back to the x's. So what you see me here is that's my u that I substitute. That I substituted right up there. So I'm picking a u. It's just like the chain rule working the other direction. Remember what we did with the chain rule to begin with? Let me just write something up here at the top. Remember the chain rule, 5 times x squared plus 4. We treat this like a variable for just a second, right? And then we deal with that variable by doing the chain rule, multiplying by the derivative what's inside. It's the same basic idea. We're treating the inside part of the composite function as one single variable. How are we treating it as one single variable? We're treating it as one single variable by making that substitution and making it one single variable. Okay. So you can see I got 1, 2, 3, 4, 5, 6, 7 different problems. I won't do all of these. I think these all might be in the book, actually. So we'll just kind of go back and forth here. Actually, I have my sheet here, so I'll just look here. So we're going to start with sine x e to the cosine x. I'm just going to do as many examples as I can in the next 5 or 6 minutes where you can see how these work, because you are going to have to wind up guessing a little bit. So first things first, we make u equal to something. If all else fails, make it equal to the inside part of the composite function. I see a composite function here, do you? I see e to something. Right? It's not e to the x, it's e to the cosine x. So this is the inside part of a composite function. So that's one thing to look for. The other thing to look for is, remember, this is going to be something different is going to happen now. So watch this. Du, because you're like, oh, what about that sine x? But watch. Du would be negative sine x dx, which means dx. So this is really good, right? Because what's going to happen when I go back to substitute, I get sine x. I get e to the u, but I still got that sine x in there. Like, whoa, wait a second, what's going on? I got two different variables. However, remember my dx is du over negative sine x. So that's going to cancel with that. So the other thing you're going to kind of see, you notice how that happened, is the inside part of the composite function, that cosine x is the one I picked, but also look at that sine is its derivative. Forget about the constants, the negative doesn't really matter. So if you see the derivative of something in a problem, that's pretty helpful also. So this now simplifies to negative e to the u du. And now I'm ready to integrate, right? I've changed the variables. And I've got rid of the composite function. The integral of e to the u is just e to the u. And then I have to substitute back e to the u, which is cosine x. You can do it like other problems. You can check your answer. Watch this. So let's check my answer. Take derivative, right? You don't really want to do this every time, but I'm going to do it. It's kind of fun. I get e to the cosine x. Derivative is e to the cosine x times the derivative of that cosine x, which is a negative sine x, blah, blah. And you get sine x e to the cosine x, which is the original problem. So some of them are really easy to check. Some of them aren't. If they're kind of more complicated, I probably wouldn't check it. Alrighty. So let's go with one more that looks similar, and then I'm going to give you one that looks a little different. So we're going to go, let's do this one, x squared times the square root, because these are the most common ones. The most common ones, it's really easy to see the composite function. I see the composite function. So I'm just going to start with that, 5 plus 2x cubed. That x squared is also good hanging out in front. You'll see why in just a second. But remember, start with the inside part of a composite function. If there is one, you're going to see in the next couple of problems there might not be. So this is 6x squared dx. dx is du over 6x squared. So now when I come back here, I get x squared, I get u to the 1/2, and then this dx becomes du over 6x squared. Cancel, cancel. It doesn't always cancel out nicely. Sometimes other tricks are going to happen. I can't even prepare you for all the things that are going to happen in these things. Some are pretty straightforward like this one. Now you're just left with u to the 1/2 du. We integrate that, which is u to the 3/2 over 3/2, or times 2/3. And then we put the u back in, which is 5 plus 2x cubed to the 3/2. Okay. So there are lots of other things that can come, and these are the most basic ones, of course. Pick the inside part of the composite function, find du. It's probably going to cancel with something, but sometimes it doesn't cancel, but that's still okay. I'm just going to kind of say that some of those things and let them happen later on. Here's an example that doesn't quite look exactly like a u substitution, but it is. I have no other way to do this problem. It looks pretty simple. It's like, what am I going to do? And this is going to be the hardest thing about integrals for you, is try to figure out what method to use and all that. So this is actually u substitution. I don't see a composite function at all. There is no composite function. However, I do see a function and its derivative. So remember all these other things. Function 5 plus 2x cubed, derivative was x squared without constants. Constants don't really matter. Here, derivative, u cosine, derivative sine, right? So here what I see in this one is I see a function and its derivative. I see x squared minus 4, and I see its derivative, which is x, or 2x. The constant again, it's just going to factor out. So I'm just going to make u equal to x squared minus 4. du is 2x dx. So this is a little bit weird. Doesn't quite look the same for you, but it's still going to work out, because watch what's going to happen. I get x. That's my u, is the x squared minus 4. The dx becomes du over 2x. Cancel, cancel. I get 1/2, 1 over u du. Integral of 1 over u is natural log of u, but u is x squared minus 4. Okay. So little twists, just the more we do, you might not get them all the first time for sure. And I could sit here and do lots of examples. And then if there's a new one, it's going to be different anyway. So I'm going to kind of let you float around with that a little bit and try. If all else fails, just guess. Just guess something for you and try. If it doesn't work, guess something else. There's usually not too many things you can guess for you, 1 or 2. Main thing is look for that composite function. It's going to show up in a lot of places. If that doesn't work, then look for a function and its derivative. Like I said, it's going to be a little tricky, I think, some of them the first times, and little different twists will happen in the middle of them. So you just have to be prepared for the other things you already know, right? Anything that you already know could also show up in these problems. So good luck, and we'll go over in class.